Welcome whoever is online. And today I will be talking about hadronic structure. As you can tell from my title, my name is Tommaso, and I'm a PhD student at El Dominion University in Virginia. I come from Italy though. And yeah, like I said, today we're just gonna understand a little bit of what hadronic structure is and how we deal with that. So let me just go into it because maybe many of you don't know what a hadron is. And so a hadron is nothing but a composite subatomic particle that is composed of what we call quarks, antiquarks, and that are held together by the strong force, by the gluons, and we'll see later what that means. Now, the word itself comes from the ancient Greek, and you'll find that basically in the very first page of Wikipedia, for example, hadros, and I'm sorry if I mispronounce this because I'm not Greek, or I never studied really ancient Greek, but it means stout, thick, and strong, which is very, hence the name strong force. Now, most of you might know particles such as the proton and the neutron, which are the elements, what you find in the nucleus of an atom, for example. And those are hadrons themselves. But there are many, many other particles that are produced by the strong interactions. I honestly myself don't know them all, but there are really many, many more. And the most common ones are protons and neutrons. Now, you probably have already seen this chart here, which is just all the fundamental particles that we know of, and they are combined in what we call the standard model of particle physics. And you see here they have different colors, and each one represents a different thing. They're named differently, and QCD actually doesn't deal with all this, but only deals with the purple particles here, which are known as the quarks, and their corresponding antiparticles or antiquarks. And we know that there are 6 flavors, what we call flavors, or if you want, 6 types of quarks or antiquarks. And the strong force also deals with the gluons. Actually, the gluons are the carrier of the strong force. If you want an analogy with the probably most a better known force, which is the electromagnetism, the gluons are similar to the photons, which are the carrier of the electromagnetic force. But the gluons carry the strong force. And so they interact with the quarks and antiquarks to form what I've just said, the hadrons. And so the QCD is all this. Now, in particle physics, we often like to describe everything with one single formula, or at least what we say, it's sort of the generator of all the physics. And here is the name is called the Lagrangian of QCD, which is where everything comes from if you want to study the strong interaction. However, this very simple looking formula, which is just a one line, one equation, really one line. From here, you can extract, in principle, everything that's related to quantum chromodynamics, the strong force. And you see here, I've just highlighted, I'm not going to explain this formula, but I just wanted to show you that really this first 2 terms are describing the quarks and antiquarks, and the last term, the gluons. And so from here, like I said, somehow with the rules of quantum field theory and quantum mechanics, you can extract in principle anything. Now, why am I saying in principle? Because it turns out that QCD is really very, very hard to solve. And my intention here is to understand how from here we get to the hadronic structure. So basically, how do quarks and gluons recombine, interact to form, let's say, a proton or a neutron or a pion or whatever else you want to study. And it turns out that this question, although it seems pretty natural to ask, it's really very, very difficult to answer. And the problem is that I'm just going to briefly go over some basics of QCD and why QCD is very hard to solve. And that is because I've just talked about quarks, antiquarks and gluons, but when you do experiments, you never observe these particles. And that is because of something called color confinement. Now, I'm sure you've already heard of this in the previous lectures, but I'm just gonna say this again, because it's important to understand that we describe our theory with some degrees of freedom, the quarks, antiquarks, and gluons, which really we never observe. If you ever do an experiment, you'd never see a free quark or a gluon. And again, let me go back to quantum electrodynamics to make an analogy. What do we mean when we say color confinement? We imply that whatever we see in the experiments does not have any color. Now, that doesn't mean that it's not the regular color here. It's actually a color charge, and it's equivalent in a sense to the electric charge that you see in quantum electrodynamics. So quarks, for example, carry an electric charge, but they also carry a color charge. And that is what it makes it interact with the gluons, which also carry a color charge. However, since I've already said, because of color confinement, you can never see a color full, in a sense, particle. You will never be able to see that. So whatever happens, let's say you see a proton, that will have to have color 0, and indeed it has. Now, a second difficulty of QCD is that, as the name suggests, is very strong. And in fact, here I'm just listing the comparison with the other known forces. And so if you look at the strength of the coupling, so really the strength of the interaction, we normally refer to it as the coupling constant of QCD, QED, and whatnot. That is of order 1. The electromagnetic force is more than 100 times weaker, and the weak force is 1,000,000 times weaker, and gravity is the weakest of the bunch. It's really 10 to the 39 times weaker than QCD, than the strong force. And so it just shows you that it's a very strong interaction. And so the problem here is that we as physicists always like to rely on what is known in perturbation theory. And explain briefly means that we would like to assume that actually the strength is relatively small, so that we can basically find an approximate solution to whatever we want to study, because we express that in powers of that coupling. And so, for example, let's say that the coupling is 1/2. If I square it, it becomes 1/4, and if I square it again, it goes to 0 pretty rapidly. But if you square 1, if you take 1 and you multiply it by itself many times, you always get the same answer. And so that means that you cannot neglect anything, really. You cannot truncate your series, at least naively. And so it seems like that is a big problem, and it is. We'll see later how we deal with that. But let me just tell you that QCD is also difficult because the gluons themselves, like I told you already, have color charge. They carry the charge, the color charge themselves, which means that they can interact with themselves. And the photon, for example, in QED do not. The photons are not electrically charged, so they interact only with charged particles, but not themselves, unlike the gluons. So all of this mess really complicates the matter, and also it entails that we really don't know how to solve QCD, that just by with pen and paper, if you wish, or even just by relying on perturbation theory. Now, there was a great discovery, though, in the past, in which the Gross, Wilczek, and I forgot the last one, I'm sorry, but in 2004 they were awarded with the Nobel Prize. And this is the so-called asymptotic freedom, which essentially means that the strong force, yes, it's strong, but if you look close enough, so if you look at very small spatial resolutions, or in other words, if you are at very high energies, the coupling, you'll see the effective coupling that these quarks, antiquarks, and gluons feel is actually smaller than 1. It's much smaller than 1, and it actually goes to 0. The higher the energy. So if you have, let's say, 2 quarks together, if you put them close enough, they will feel very little strong force. But if you try to pull them apart, that's where the coupling becomes strong, and it's really very hard to pull them apart. But this means that when we have a small coupling, then we can rely on perturbation theory, which in addition means that we can predict something finally with just our perturbative calculations. Now, obviously, this is not the whole picture because, like I said, this is true only at very, very high energies when you can have that the coupling is small, but it's not always true. Now, here I just want to show the what I've just said, but the experimental evidence for that. And this plot shows the what we call the running coupling constant of QCD. So literally the strength that you see depends in the y-axis. I have the coupling, and in the x-axis I have this Q, which stands for the energy of the experiment, for instance. And you see that it decreases the higher the energy. Notice though that this is a log scale. And so everything is stretched, like actually it's compressed. And so the coupling does get weaker, but it gets weaker pretty, not very rapidly, really. It's pretty slowly. All right, so this was a very brief introduction of QCD, which again, you have probably heard about these topics many times. Let me go into the main talk of today, which is actually the hadrons and their structure. So I am interested, like I said, in what is the internal structure. So if you think of the proton, you might think of a ball, and inside it might have quarks, antiquarks, and gluons, but we want to address that mathematically and rigorously. And so how do we do that? Well, it turns out that in the early 60s, there was this notion of flavor symmetry, which you've already seen in the previous lectures. And by relying on this symmetry, you can sort of categorize your hadrons into these objects, which are the representation of a group. But for those of you who don't know, it doesn't really matter. It just turns out that if you believe that this flavor symmetry is true, and it's actually almost true symmetry in QCD of nature, it turns out that you can have all this zoo of hadrons that will be at these, the vertices of these polygons. And you see there are many, many names that I don't even know, honestly, all of them. But the point is that if you believe that this is true, and this is like a quasi-symmetry, it turns out that this tells you that the neutron and the proton, which you can find here, I hope you can see my cursor, should be, you see, if you look at the neutron, the flavor symmetry tells you that it should be one up quark and two down quark. And the proton should be two up quark and one down quark. And obviously you can see all these other, the pions, the eta particles, and so forth. There are really many, many hadrons. And so if you just rely on flavor symmetry, you would end up with a picture like this for the proton. So it's a ball composed of two same balls of U up quarks and one down quark. And so if the flavor component of that would be two up, one down. The charge, if you just sum everything, turns out to be 1, as it should, because the proton has charge +1. It's in a configuration such that the spin of the proton is 1/2. But you should remember that also all the quarks and antiquarks are also spin 1/2 particles. And most importantly, they are in a combination such that the color charge is 0. However, this is very nice. Everything that comes from a symmetry reason, it's very nice because we can really understand what's happening, how to categorize things, but reality is actually much, much more difficult than this. The proton, let me tell you, is not just two up quarks and one down quark. And that is because of quantum field theory and the rules of quantum mechanics. Now, reality looks a little bit more like this picture that I'm showing here, which I have taken from the CERN website. And you see that you have everything really. You have all the possible quarks, all the possible anti-quarks, and the gluons themselves. That somehow is a big open question. Well, not really open. That's what we try to do. But you really have all the possibilities that come from the rules of quantum mechanics. Now, for fun, I have also tried asking an AI, since it's very common nowadays to rely on AI, an AI image generator to tell me what the structure of the proton, for example, is. And these are just a couple of results that it gave me. This is from Bing. And it looks, I have to say, it looks pretty nice, but obviously I cannot extract any physics from this because, well, first of all, it's definitely not true. I don't know how to interpret it, but it really does look very, very nice. Much nicer than the picture that I've come up with here. So really, anyway, this was just for fun. The point here is that quantum mechanics, quantum field theory in general, this is not just about QCD, is very weird because it doesn't really rely on your naive expectation. For example, QCD tells you that if you have a quark, let's say that you have a propagating quark this way, you can think of this as time going from left to right. At some point, that quark can split up into, well, it can radiate a gluon in a certain direction, and that gluon can split into let's say a down quark and an anti-down quark, or actually it could split up in any anti-quark and anti-quark. Or another instance could be that a gluon splits into quark anti-quark and then it recombines to form another gluon. And obviously you have all these rules and all these graphs that you can combine together. And for example, here I've just combined these two down here, so you can have a propagating quark that emits a gluon, it splits and recombines, and it finally gets back to the quark, and so forth. You have all these nested graphs, and the thing is that you have all of them. You cannot neglect them. You really have all of them, and that is the problem. It's not just one freely propagating quark. It's everything. Now, this looks like a mess. We don't, at least if you know of this, it really looks like a mess. You don't know what to do, or at least you think you don't. But there are many, many ways to tackle this, stemming from the framework of quantum field theory. There are many ways to try to solve QCD. Now, you have probably heard of lattice QCD, which in very briefly tries to solve the strong interaction by relying on computers that discretize spacetime and simulations on computer that discretize spacetime, and they try to solve QCD like that by taking the infinite volume limit, for example, basically taking the spacing to be very, very small and the volume large. There are other ways that you can tackle QCD not from the fundamental interaction, so not from the Lagrangian of QCD, but from what we call effective field theories, which are very, very useful. But what I do is called factorization, and it's a really very well-suited framework to study hadronic structure. And I'll address that in a few moments. But essentially, the nature of factorization and the scope of it is to really disentangle the perturbative component of an observable with the non-perturbative component. And for those of you who don't know what this means, it essentially means we want to try to understand how to disentangle the part that we know, that we can calculate, and we know what it is and where it stems from the part that is actually intrinsic to the hadron itself, which tells us about the structure of it. So, how do we do this? And like probably most things in particle physics, we look at experiments, and we look at scattering experiments in particular. So we like to smash particles together and see what happens after that. And we can reconstruct what happens. Our theory, our framework tells us what means, whatever we end up with, what it means. Here I am just listing you see in this box, I'm just listing a few of the possible scattering experiments that for which a factorization theorem exists. That means that for these experiments, and they have these names, DAS, cities, SIA, and DY, and DY, which stands for Drell-Yan, you can prove that you can, like I said, disentangle these perturbative and non-perturbative contributions. Now, I will not be talking about all of these. Actually, I'll be only talking about the first one, DAS, which stands for deep or deeply inelastic scattering. And you can think of that as an electron, for example, that strikes a target, a hadronic target, like a proton. And in the end, you see the scattered electron and everything else that comes out of that collision. And you don't really care what that is. You just sum over everything, really. And from there, there is a theorem that tells you how to get some of the information of the proton. Let's say that the target, this H here stands for hadron. Let's say that we always work with a proton, so that to make it easier to understand. Great. So before going into that, let me just tell you that this experiment have to be done somewhere. And here I'm just listing some of the few facilities where these experiments are done. For example, there's Jefferson Lab in Virginia, in Newport News, which is where I work at. There's Brookhaven National Laboratory in New York. And probably the most famous one is the LHC at CERN in Switzerland. And many, many more. Obviously, I'm just not listing all of them. But I just want to tell you that really many, many people work at these experiments, at these questions, and not just the question that I have, really many, many other subfields and fields of particle physics. Great, so let's just go into DAS and scattering experiments and factorization from here. So here I'm just showing the graph representing the scattering of an electron of a proton. So again, time, you can think of it as going from left to right. And this, let me see, where's my cursor? Here. So this you can think of as the incoming electron that, by the rules of QED, so quantum electrodynamic, just emits a photon that strikes the target. Well, actually, it strikes the component of the target, which we know should be quarks, antiquarks, and gluons. Now, when we deal with factorization, we actually don't always say quarks, antiquarks, and gluons, but we always say the partons, because those are basically the ingredients of the hadron. And so it strikes a parton, and then something else happens that in the final state, you'll see other hadrons. And this is just a scattered electron that comes off with a different angle, with a different energy and momentum. Great. So finally, we come to basically the first equation of the lecture. Well, the second, if you count the Lagrangian. But this is really the most important one. And here I'm just showing the factorization theorem for DAS. And for different scattering processes, it will be different. But this is the easiest to understand and also the easiest to really just write down. Because this tells you that the sigma DAS, you can think of just any observable that you related to DAS, so to deep inelastic scattering. Normally, we think of them as, well, we always refer to the cross-section. But really, just think of any observable. So this one to the left is what you see in the experiments, is equal to something, the sum over the constituents, and now I'm going to address that, of this blue term times this red term plus something, basically plus errors that you see if Q here stands for the energy of the experiment. If Q is pretty large, you can neglect this term. And this formula becomes just blue times red, summed over all the constituents. Now, obviously, blue times red means nothing. We have to understand what they are. But the thing is that this blue term, which we call as the partonic cross-section, is nothing but, if I go back to this graph here, I told you that the photon interacts with one of the constituents here. And that is exactly the cross-section that we can calculate using perturbation theory that would go into the blue part. So the interaction of the single with the single parton is this blue term times this red term, which is actually not from, it doesn't come from the interaction with the single quark, antiquark, or gluon, but it's something that turns out to be intrinsic to the target. And now I've said, you probably are wondering why I've put this weird times here symbol, because it's actually not just a time, you're not just multiplying the blue with the red, but it's actually we call it a Melling convolution. It doesn't really matter what it is. The point is that you see that you can really factorize, that is why I call factorization theorem, these two contributions. And the very important point is that this in blue we can calculate, this in red we will have to extract from experiments, but that is intrinsic. And to make it even probably easier to understand, let me just show you the graph here of the cross-section, really. So here, you see here, I've just neglecting the electrons, which really we don't need. That part is very easy to understand. You have a photon that will do something here when it interacts. Okay, let me just go back 1 second and rephrase this maybe better. Do you remember in the previous graph, you had a photon that interacted with something, and you had an incoming, let's say the proton with momentum p. Now, let's just look at half of this graph. So this left contribution here. Inside the proton, I said there are quarks, antiquarks, and gluons, and let's say that the photon interacts with a quark inside the proton. So it will interact with something, with this blue blob, and this blue blob is exactly what is in this formula here, this sigma ij hat. I'm showing, you see here, there is basically the mirror image to it, to the right, just because this to the left is actually what we call the amplitude, and the physical observable is actually the square of it. So you basically just fold it on the other side, and it's like the square of that amplitude is the cross section. But the point here is that factorization actually tells you how to basically split this graph in two parts. So the upper part, you see that is basically the process that's happening. The photon or the electron is interacting with each constituents, this line here and here, obviously. And then it goes away and it produces whatever it produces, all the possible hadrons. Oh, sorry, I just had a question I didn't see. Is the strong force at very near distance repulsive? So, okay, sorry, this was a few minutes ago. I apologize, Raphael. So the strong force at very near distance is not, well, it depends on the charge, really. But if you have two, let's say a quark and anti-quark, and you put them very close together, they will not be pulled apart. I mean, they just don't feel that much interaction. If you go back to the slide where I was showing the coupling, you can show that it really goes to zero. Whereas regarding Faraz, question K, so this K here, I'm assuming that this is what you're asking, is just the momentum of the struck quark. So yeah, sorry, I should have been more consistent with my explanation, I suppose. This, you have an incoming photon with momentum Q. This is the incoming proton with momentum P. And this is the, which, it's the photon strikes something inside the proton, which is a quark in this graph, which carries momentum K. All right, I hope this answered the question. Okay, so the most important thing here I just want to mention is that since the factorization theorem tells us how to cut this, and I just realized I had another, okay, great, perfect. Since it tells us how to cut it, we see that there is a process-dependent factor, which is this blue one up here, and a process-independent factor down here. Because you see, above the cut, there is everything, whatever you want. You can really actually change this up here, but this will stay the same. And you see here, this whole thing just depends on the target. This red blob just depends on whatever you are trying to probe. In my example, the proton. And since it's process independent, it is intrinsic to the target itself. Now, what is it? Because I've just said many things right now, but I don't know so far what actually this F is. So let's try to understand. Now I don't know why. Okay. So it turns out that there is a very nice interpretation to this F. And because before giving you the answer, let me just tell you this. Suppose that you have a proton that's going in a certain direction with a certain momentum, capital P here. And again, answering to the previous question, something inside the proton, any constituents, which could be quark, antiquark, or gluon, with momentum K. Now, that parton will also have a fractional momentum, of the target. And the fraction here we normally call Xi, this Greek letter Xi, or X sometimes it's called. It depends, but it's just a name. The point is that it has a collinear momentum fraction Xi, which can go from 0 to 1, obviously, because we don't want to go in excess of momentum. We don't want to violate momentum conservation. Now, normally we use this notation for F. You see that there is a sub blue dot slash yellow dot, which means the way to read this is just the F of the parton I, let's say. Actually, let me just go over the formula here. It's better to understand this here. So it's F of J. This will be the struck parton inside the hadron with momentum fraction C. Now, what is the interpretation? It turns out that it behaves, and I put quote unquote here because it's not technically the same, but it behaves as the probability distribution to find parton, that specific parton inside that hadron carrying momentum fraction C. I hope this is roughly clear. So again, you have many partons inside the proton, each one carrying a certain momentum fraction of the entire one. And if you do your DIS experiment, you extract that F, which tells you what is the distribution in terms of momentum fraction. So basically it tells you how many up quarks carry 0.1 of the initial momentum, how many up quarks carry 0.2 of the initial momentum, and so forth. It's obviously a continuous function from 0 to 1. So there is actually an analogous term which doesn't show up in a DIS factorization, but it appears in other processes, which is called the fragmentation function. And you can think of this as being the reverse, the mirror image to the parton distribution function, or PDF. So the fragmentation function is, I told you already, because of color confinement, we can never observe quarks and hadrons. So quarks and antiquarks and gluon have to recombine somehow to get the hadrons. And so that you'll see that, well, you see that the fragmentation function behaves as the probability to find the hadrons inside the quark. Obviously, there is no hadron inside the quark. It's just an operator that can be expressed or interpreted, actually, I should say, as that. And the momentum fraction normally is called Z. Great. So going back to our proton, and now that we know that if you do a DIS experiment on the proton, you should expect to see those PDFs. And if you think a little bit about it, you can sort of naively, at least, try to guess what the shape of these PDFs should be. Now, if assuming that flavor symmetry is exact in the sense that, and also there are no quantum mechanical, you suppress quantum mechanics in a sense. You just say the proton is just 2 up quarks and 1 down quark. Then if you assume that each one of these balls carries a fractional momentum, the same fractional momentum of the incoming, well, of the target, then each one should have 1/3 of it, because there are 3 particles inside there. And so you should say, okay, I believe I should expect my PDF as a function of the coupling, sorry, not the coupling, the fraction, to be something like this. For the up quark to be peaked at 2/3, because obviously I have 2 up quarks, each one carrying 1/3 of the momentum, and the down quark 1/3 because I have only 1. Now I have another question. Since we're talking about photons, are these intrinsic factor related to the hidden variables we discussed in Bell's inequality? So no, I mean, these intrinsic factors are really, I'm just calling them intrinsic in the meaning that they are, they describe the target without the complications of the experiment. Like the photon does not is not in the F. Let me just go back to this graph here. The photon here is just telling you that the DIS experiment, I'm assuming that the electron that scatters off the proton interacts electromagnetically with the proton. So it means that it just shoots a photon. So that means that there is an electromagnetic interaction, and then the photon strikes whatever it strikes. But the point here is that whatever this is, whatever you see above, it doesn't really matter, because you can prove that you can split it. And by intrinsic, I mean just this down part, which means that it does not depend on what happens up here. It's just something that is intrinsic to the target. I don't know if I'm just saying the same thing over and over, but really it has nothing to do with that. It's something that if you want, it's something that only tells you about the nature of the hadron and not the process, not the photon or whatever else. Great. So, all right, let me go back because I don't know how much time I have. I should have 37, all right. Okay, so I was saying, I'm expecting my PDFs in the proton to be like that, just because, from flavor symmetry and from intuitive consideration, I expect something like that. However, this is not really what it is. Now, just as a very simple exercise, you should be able to plot what you would expect the neutron instead, the PDF in the neutrons to be. But let me tell you that, again, whatever you think is really not true at all. And in fact, I've mentioned already that because of momentum conservation, these PDFs should have to satisfy what we call the momentum sum rule, meaning that this is another formula, and I'm going to explain what it is. So this long line here, it means that I'm summing over whatever is inside, and this C times F is just the distribution of the momentum. So if I sum over everything, I should expect the average of that momentum. In other words, suppose that I'm studying the PDF of the up quark, and I want to know what is the average momentum fraction, actually. What is the average momentum fraction of the up quark inside the proton? Then I would calculate this thing. If I sum over all the constituents, I should get 1, because momentum conservation. Like earlier, I said 1/3 plus 1/3 plus 1/3 is 1. That 1/3 would be the average momentum. So this is the naive expectation, 2/3 for the up and 1/3 for the down in the proton. This is what you see in experiments in very high energies, actually. You see that the momentum fraction of the proton is actually almost 1/3 and not 2/3, so 0.36. and for the down quark is actually 0.18. And so now you begin to wonder, well, but if I sum everything together, it certainly does not add up to 1. In fact, it adds up to 54, 0.54, obviously. And I have a remnant, something that I'm missing. I'm missing 46% of the momentum. And that is because my naive expectation is definitely not correct. And it's because of what we call the C. And the C here just means the everything else, like everything, every other quark, anti-quark, and gluons that I have not addressed. Great. So here, I just want to really show you, because I've been telling about experiments and extraction of, I mean, these PDF, they have to be extracted from experiments. So let me just give you what we get from them. And first, let me show you, remember earlier I showed the expectation, and here I'm just in this plot shows the C times the PDF, not just the PDF itself, as a function of the momentum fraction. And again, this is a log scale. So 1 is here, and 0 would be at -infinity to the left. But the point here is that my naive expectation, which are these dot dashed curve, blue for the down quark and yellow for the up quark, are definitely not, definitely very different from what we see experimentally. Now, here I'm actually showing 2 sets of PDFs. And so you might wonder, okay, why am I showing 2? Isn't just the PDF for the up quark 1? Well, yes and no at the same time. And it turns out this is because, like many other things in quantum field theory in general, whatever you observe, whatever you extract, well, not everything, but many things actually depends on the resolution. And so, in other words, it depends on the energy scale. And so do the PDFs. So you see here, I'm plotting the PDF of the up quark, this solid yellow line, sorry, at 3 GeV. But when I increase the energy, it becomes like this. And so you see actually from here, you can tell that there are more up quarks carrying lower momentum fraction, higher energy than the lower energies. And so the same basically happened for the down quarks. And now they're actually all the others, which I'm not showing here. I'll be showing at the in the final, after I finalize the presentation. I'm going to show you all the other PDFs that are there, the strange, the anti-strange, anti-up, the gluons, and everything else, really. All right, so let me go. I've just said that things are not like we expect, but we know that flavor symmetry is roughly true in the sense that it's a quasi-symmetry of nature, and also it's when we from experiment we let's say we measure the charge of the proton, we measure it to be 1. And in the quark model, you have that, if you have 2 up quarks and 1 down quark, we'll see, we saw earlier that it does add up to 1. So what we mean now, how do we reformulate, or if you want to interpret flavor symmetry combined with this notion of PDFs? Well, if the PDF has to be interpreted or can be interpreted as the probability distribution to find that specific parton with a certain momentum fraction, then if I sum over everything, over all the possible momenta fractions, I should recover the number of that specific quark inside the hadron. And so this formula tells you that if I sum all the quarks in the hadron, all the up quarks in the hadron minus the anti-up quarks, I should get 2. This is what I expect, which traces back to this picture, 2 up quarks. The same for if I sum the PDF of the down quark minus the PDF of the anti-down quark, then I should get 1. And all the rest, whatever it is, should sum up to 0. These are like averages. Like on average, in a sense, I have 2 up quark. On average, I have 1 down quark. And on average, I have 0 everything else. I have a question. Yeah. what are the main principal equations that govern quantum chromodynamics? Okay, well, that is a big question. But so if you wish, at the beginning, I just said that we have that simple looking equation Lagrangian, and from there you can extract everything regarding quantum chromodynamics. Now, this really is not a question that I can answer in not even in an hour, I believe. But let me just say that apart from quantum chromodynamics, any quantum field theory can be described with a Lagrangian, and we do know the rules from that Lagrangian how to get whatever we want in principle. The problem is that we don't know how to solve it. Like, we know how to solve it formally, but we don't know how to explicitly find the results or even just try to compute it. That's why we use lattice factorization. We just do many things. But the main principles of quantum chromodynamics are just the same as quantum electrodynamics, in the sense that, or I should say quantum field theory, really. We rely on quantum field theory. That is the main framework, in a sense. I know this probably doesn't really answer you, but it's a complicated question, really. So maybe let me just finish this, and after this, I'll just get more questions. All right, so this was for the proton. You obviously can do the same for the neutron. You can do the same for all the other particles, the pions, the kaons, and whatever else. Let me just show you a very brief. So this is a video that I found online by REYES at MIT, and it's a very nice video because you can visualize what happens. It's obviously an animation, a simulation of what happens inside the proton, but it's a very nice video because it shows that when you increase or decrease the momentum fraction, you have different pictures, and also when you increase the energy, you have also different different results, in a sense. Now, I'm not going to show all of it because it's a long video. I'm just going to show the first 30 seconds. If you want to see it, you can click on this link, and for more information, you can just go here. So let's see if it works. Right, so you see that at very small momenta fractions, you see everything going on, like a myriad of things going on. If you increase it, you go, in a sense, toward the more familiar notion of two up quarks and down quarks. And if you recalled earlier, the peak of those PDFs were, I mean, you had a lot of quarks and antiquarks at very low momenta fraction. And then, okay, yeah, this is this similar plot. See, you have at q squared equal 200 GeV, you have very few particles at up and down quark, I should say, a small momenta fraction, and a lot of them here. But you see that these other curves, which I had not shown earlier, are the rest. So here is I think this is probably the C without the gluons, and this is the gluon, or this is probably the strange. I don't really know. I would have to look it up. But you have everything else. And this is not surprising. Let me just go back here for a second. That at very, what is this? At very, you have a lot of very small, I'm sorry, let me rephrase that. You have a lot of gluons, for example, carrying small collinear momentum fraction, as well as the rest. The thing is that they all have to, whatever it is, they all have to satisfy these sum rules, actually. And this is the number sum rule. There's also the momentum sum rule. Remember this one? And there are also additional constraints. But yeah, that's how it looks, really. Let me just show it again. And then we can, I'm almost done, really. I hope I'm not going too late. See, it's a very nice picture. And there you see, you increase the momentum fraction, and you see that. All right, so what I've said and talked about so far is just a tiny dot into the realm of factorization. because today I've actually talked about the unpolarized Parton distribution function, or PDF, that F that I showed earlier, the red F. Now, it turns out that there's actually way more to the picture than what I have described. Now, unpolarized here stands, if you can think of it as, basically we have neglected the spin of everything. I did not care about the spin of the proton. I did not care about the spin of all the other particles that I was talking about, because I've taken a spin average over everything. And that will give you the information about, well, this F gives you the information about that. But obviously spin is there, and you can prove that other factorization theorems, or even just the REYES itself, will have also additional terms if you are interested in the spin degrees of freedom. And you have all the possible combination, because spin is not a number. It's actually, you can have it longitudinally polarized, you have transversely polarized, and you can have all the possible combinations. And the what I'm showing here is just all the possible distribution functions that you have, and similarly fragmentation functions. And they all have different names. Some of them are very weird, and I don't really know why, like worm gears, velocity, very weird name. But really, what I've just said is just this dot here, and this is only talking about collinear distributions. Actually, there is way more than that, because you can think of the structure, like the partons inside the proton, not to just go along the proton itself, but they can also wiggle around with carrying certain transverse momentum. And also, instead of looking into the momentum space of the distribution, many people work in the actual space, in the coordinate space. And so, for example, today we've actually only talked about this dot here, but I'm showing here that many people work at all these possible combinations of, on top of just spin, not spin, longitudinally polarized, transversely polarized. There are also other degrees of freedom instead of just the momentum fraction. Here, for example, TMD deals with the momentum fraction and the transverse momentum, or the GPD, for example, deals with the spatial. If you want, you can think of it as the real picture of the proton, of the quarks in a proton, and so forth. There are really many others. Now, I don't know if I should stop here, but I just had a very brief sort of in a work that I've worked on a paper, and we have studied a toy model instead of real QCD, just because some things about factorization is easier to see there instead of deal with all the complications. And so I just wanted to show briefly that factorization does work, and also one extraction of the PDF when you can see. So this is really, and if you want to find it, there is, and if you have Mathematica though, because this was done as a package for Mathematica, you can find it here. So let me just go there and show you briefly, and then I promise I'll stop talking. And thank you. So let me see if I can figure. Hold on a second. Let me see if I can get it. Yes. All right. So let's see. So this is the I promise I'm going to explain what I'm showing. One second. I just want to make it big so they can all see. So I said I'm going to study a model that is not QCD. I'm just using let's assume that in this specific model there's just one target, one quark, and one scalar field, which could be like a meso-appian, for example. And if you calculate the cross-section, or actually this is part of the cross-section, you will end up having all these nice little curves. So this is just, you can think of this as the cross-section as a function of xc or x. Here I've called it x, but it's the same xc. And for different energies, that Q that I showed earlier. And you see they do whatever they do. This line here is just a kinematical cut. that, for example, this blue line cannot go over past this line. Now, this is doing exact calculations, okay? No factorization. The thing is that if you recall the formula of early, we should be able to use factorization to approximate these curves. And it turns out that if we do factorization, these curves look like this. And these are the same curves, I mean, the factorized curves, but at the same energy for the same momentum fraction. However, you see now that I've just left the kinematical uppercut. But, you know, the approximation don't know anything about these lines, the kinematical uppercuts. And that is to be expected because we are approximating something and so we don't have the whole picture. So some things we lose. But the point here is that when we try to compare the two, and this is just the comparison, you see that for sufficiently large energies, so this here, for example, 20 GeV, this last curve here is very well approximated by the dashed curve, which is the approximated factorized version. And so this tells you that, first of all, factorization works, and indeed that it works better when the energy, is high enough. Because you see here, this is the lowest energy portion of the lowest energy observable that I've decided to put here, and it's not really well approximated by the factorized this dashed curve. And so this is really was just a way to show you that factorization works, and here you can explicitly see it. In QCD, obviously, we can calculate and extract these dashed curves, but we do not know, we cannot calculate these solid curves because we cannot solve QCD. We have to rely on something else, namely factorization or lattice QCD or whatever. And finally, in this model, the PDF turns out to be something like this. Well, this is actually C times the PDF. And so you see it's roughly the same as earlier. All right, this was really a very brief note on this, and I believe I can stop talking because I've talked long enough. And thank you all. If you have any question, please let me know and just ask. All right. I don't think there are any more questions. It seems. I don't know. Yes, there is some questions. Let me see. So should we submit a report or something? So yes. So the usual optional weekly reports you can submit. And so yes, if you want to, you can and you should. And regarding also the final presentation, I've already mentioned at the beginning, probably not everyone was here, it's optional. However, if you decide not to do it, you should email. I believe that Dimitra had sent an email to everyone saying that you should contact her. You should just tell her if you don't plan on having that presentation submitted. And yeah, let me just read it again so that everyone, we are on the same line. But yeah, essentially it's optional. The final is definitely optional, and the the weekly also, you'll find everything as usual in the Dropbox folder. And I'll create my own. I still have not done that, but I will. And so yeah, I believe that's it. Let's see if there's any more question. So how does asymptotic freedom play a role in the behavior of quarks and gluons according to QCD? So so essentially it tells you asymptotic freedom means It's just a fancy word that tells you that the coupling, so the strength of QCD, of the of the interaction, gets small when you go to high energy. So that just means that you can have free, if you go at extremely high energies, which are not, we cannot ever achieve here, at least, well, maybe one day, I don't know, but probably not. You will see free propagating quarks, antiquarks, and gluons, but that is at extremely high energies. So effectively, if you are not, namely actually infinity, the coupling goes to zero at infinity. So when the energy is infinite, which obviously never happens, we don't have infinities in nature. If not, it just means that you will have, you will never be, well, you don't have free propagating quarks and antiquarks, and the strength is always non-zero. It's just something. But it can, you know, it just affect the strength that they effectively feel is less when they're close, and very large when they're apart. Now, obviously, apart here doesn't mean 1 meter or our scale, it's subatomic scales. Also, QCD is a short range force, unlike QED. So we are talking about Fermi and even less. Is there another question? So where should we submit those reports, and what should it contain? So the reports you should submit in the, like everywhere, sorry, like in the past on Dropbox under your name. You should have your, you know, your folder, and it should contain whatever you want, really, whatever you got from this lecture. I didn't really add any exercises, or at least they were pretty simple. So you can just write down whatever you have understood, whatever you prefer, really. And it is for the certificate. Yes, it's 1 second, sorry, because what's happening here? Like I said, let me just re-say this. The weekly submission is optional, as well as the final presentation. However, everyone is strongly encouraged to do that. And obviously, if you want to for the presentation to receive the certificate, you should be able to at least provide something, at least something written, of course. Yes. Oh, sorry, I got other question. I'm sorry. So the weekly is, if you want a certificate, you have to do it. But it's obviously optional. No one is telling you that you have to do it. If you want a certificate, yes. The presentation, on the other hand, is not. But you should email the matron. So the presentation can be on anything that you have learned over the whole program. And you can just do, and also you can work with someone else. Maybe you can just present some of the exercises, or just come up with some of your own. Just do a briefly, really, whatever you feel like, as long as it shows that you have understood and you have just attended these lectures and what you have come up with. what are, all right, so I have this, what are some experimental methods used to validate the prediction of quantum thermodynamics? Well, I'm not sure what you mean by that, but we normally, it really depends on what you ask. What I do to determine the hadronic structure can be done in many ways, really. Factorization normally is just you rely on scattering experiments. So whatever you see on at colliders like CERN, like Jefferson Lab, and so forth. So you rely on those. Let's say that they measure a cross section. That's what they do, and you from there. And let's say they study DIS. From there, you can extract, well, use your factorization theorem formula, you can extract the PDF for the upworks, let's say, and then in another experiment that still has that, it's a different experiment, a different probably even process. Well, yeah, a different process. You still have to use that specific PDF, and you can inject the extracted one into the results of these other experiments. And since it's an intrinsic quantity, they should be all the same, regardless of whatever experiment you're looking at. And so in that way, we can validate the specific case of factorization. This actually has a name. It's called universality of PDFs, because universality is just another way of saying that they are intrinsic, that they only depend on the target and they don't depend on the process. So you can just study different processes, and the hope is that the PDFs are all the same, because they should. So I don't know if this answers the question, but at least in the tiny subfield of factorization, this is what we do. It's a pretty broad question, though. All right. Any additional question? All right, I believe that that's it for today. And next week, as I understand, there's going to be the last lecture of the nuclear physics mentor program. So thank you all for attending. And I believe that we can end it here. I'm just, I don't know if I should end the meeting or the host.